Welcome to Hephzibah Simple Class. Today I will be talking on lactose operon. In one of our previous classes, I already talked about an operon. I said an operon is a unit of genes which are under the control of a single promoter where RNA polymerase binds. These genes are transcribed togetherly at once. However, a lactose operon or operon is a unit of three structural genes that are involved in the transport and catabolism of lactose. These three structural genes are transcribed at once under the control of a single promoter. The operon is however required by many enteric bacterial cells like Escherichia coli for the transport and catabolism of lactose, a sweet disaccharide sugar made up of galactose and glucose, commonly found in milk and dairy products. Lactose is converted to allolactose by beta-galactosidase in an alternative reaction to the hydrolytic one. Although glucose is utilized preferentially as carbon source for most bacterial cells, when glucose is not available or when the cells are starved of glucose, the available lactose is effectively utilized through the activities of the enzymes encoded by the three structural genes on the operon. The three structural genes are designated as LacZ, LacY, and LacA. LacZ encodes beta-galactosidase, an intracellular enzyme that cleaves lactose to galactose and glucose in the hydrolytic reaction. LacY encodes beta-galactoside permease, a transmembrane enzyme that pumps beta-galactoside, including lactose, into the cell. In another word, the beta-galactoside permease increases the permeability of the cell membrane to beta-galactoside and lactose. LacA encodes beta-galactoside transacetylase, an enzyme that transfers an acetyl group from acetyl-CoA to beta-galactoside. Now let's see the regulation of lactose operon. The structural elements of the operon is made up of structural genes, operator sites, the promoter sites, and regulatory gene, including the catabolite activator protein binding sites. Thus, lactose operon in bacterial cells is regulated in the following ways: presence of glucose and presence of lactose. The presence of lactose causes allolactose to bind the repressor protein, and the presence of glucose causes cyclic AMP level to be low. Thus, catabolite activator protein remains inactive, and catabolite activator protein cyclic AMP complex is not formed. Though RNA polymerase binds to the promoter site but keeps falling off from the promoter, and therefore transcription occurs at a very low level considered insignificant. Presence of glucose and absence of lactose. The absence of lactose causes the repressor protein encoded by the regulatory gene on the operon to bind to the operator sites, and the presence of glucose causes cyclic AMP level to be low. However, the binding of repressor protein to the operator site prevents RNA polymerase from binding to the promoter site, and therefore transcription will not occur. Absence of glucose and absence of lactose. The absence of lactose causes the repressor protein to bind to the operator site. Although cyclic AMP level is high because of the low level of glucose. Thus, an activator, catabolite activator protein, is active and builds a complex with cyclic AMP, which subsequently binds to the catabolite activator protein binding site on the Lac operon. But the binding of the repressor protein to the operator site prevents RNA polymerase from binding to the promoter site, and therefore transcription will not occur. Absence of glucose and presence of lactose. The presence of lactose causes allolactose to bind the repressor protein, and the absence of glucose causes cyclic AMP level to be high and to build a complex with catabolite activator protein, which binds to the catabolite activator protein binding site. This thus makes the promoter site free for RNA polymerase to bind, and therefore transcription occurs. Here I come to the end of this class. I want to acknowledge and appreciate authors and owners of every image and material used in this class. Thank you.